you so much. As said, I would like to be challenged because I have rarely had an opportunity to be talking into much more detail about the structured atom model. So anything that pops into mind. Specific questions about elements, that would be nice. Radioactive decay, all kinds of physical properties, chemical properties. So it's all good. Just now before this moment now, we were having a coffee break. There was a nice little interaction already, where I pointed out that the carbon that we see here is an icosahedron shape. So the icosahedron is one of the platonic solids. What I pointed out, which led to some enthusiasm already, is that the dodecahedron is around this. Now, what am I saying? The icosahedron here is a proton structure, meaning all positive charges, if you will, that could never be on its own. Because the protons are in the nucleus with the official mainstream neutrons, they had to think of a way how those positive charges could stick together. That led to the strong force. So the strong force is done away with in this model. Now the icosahedron creates the possibility for the dodecahedron, the last platonic solid, to be there. And what I pointed out is that the dodecahedron on its own, which is considered a platonic solid, cannot be on its own. And that dodecahedron can be when it's supported by the underlying proton structure. So the proton structure, which we see here, which is what the depictions are from the structured atom model, is one of the coin sides, if you will. The electron, the dodecahedron structure, is the other side of the coin. Now, an atom can only be there in a stable state when both are there in equilibrium. Now, that's a key point I try to make in personal conversations, because when that happens, when the dodecahedron is there, so the electron structure around it, that's when we reach the noble gaseous state. The noble gaseous state is an atom which is complete on its own, doesn't need anything to be complete. So atoms that are reactive, they need each other to balance the forces again. Then they become noble-like, like a noble element. Only in this case, it's a combination between two elements which we call chemistry. When that happens, things radically change. A good example is carbon again. It's the blackest substance we know. It's used in the black body model and all that. And it's graphite, it's very dark, it's totally black. And when it changes into diamond, it becomes suddenly totally transparent. If we take a CO2, very known chemical compound, the C and the O combine, and suddenly it's totally transparent, it's in the air. So when this happens, when this dodecahedron is created, supported by the underlying structure, which is the prevalent repeating structure in the atom model, that's when the substance changes from black to utterly transparent and noble. Noble meaning I can be on my own. So that's kind of my introduction. We have a list on the right, which has the elements that we created so far. This list is even longer than the list we already published, as you can see. It's not complete, definitely not. When the elements become heavier, it becomes very difficult because, if only due to the number of possibilities. So it becomes a bit difficult for the mind to be very specific. I guess this is where my short intro would stop, and I would like to ask you if you have any questions. So please grab a mic and we'll start the debate.
We were talking amongst ourselves earlier about alloys. Do you have any examples of alloys on there and how they fit together?
No, would be the short answer. We haven't reached the level of chemistry yet. What I'm saying here is, this is still the atomic physics model, but we do make a very strong connection and explain how chemistry works. I was just alluding to that, right? This model needs a lot of work, and we need to step up also, so go to the chemistry level, if you will. That means future versions of this builder that you see here. This is the first one. This is being created in the past 2 years, just about. And so I cannot do that yet, but I can allude a little bit. James, could you, let's see, Can you go to chromium or something? It's a little bit up, and it should be, where is it? There it is. Okay. Right, this is the good example. Elements have properties, right? That's what you're after. Elements have all kinds of properties. The noble gases I just mentioned. We have the alkali metals, which is a +1 metal, like lithium, sodium, potassium. Then you get the next row, it's magnesium and calcium, for example. And they have suddenly two connections. Now this one here has 3 active nucleates, represented by the colors yellow and blue in this case. So the white is neutral, doesn't participate. We can see several things here. This has to do with the properties of the elements. That's the connection we're trying to make. Now, the yellow one makes usually, not always, usually 2 connection points, meaning 2 valence electrons in the chemistry terms. But we have already 2 of them, and we have another carbon, the blue one. The blue one can have 4 or 2 connections, either positive or negative, depending on the circumstances. Now, this is a chromium, and we know that chromium and vanadium as well, they are metals that are used in all kinds of protection for your tooling, for your hammers and your screwdrivers, etc. They're highly resistant to corrosion, they're very strong, etc. Now, why are they strong, right? Why is one alloy or metal, why does that make a strong connection, the other one doesn't? Well, chromium has not only at least 2 and another probably 5, 6 connection points, which is the oxidation state or the valence state, if you will, but it also has 3 points really in the dimensions. So when this thing is done reacting in the chemistry, it has many hold-ons, if you will, many connection points, rigid connection points. That's where the strength of that alloy comes from. So I hope to have answered your question, at least in that way.
2 kind of points. I wondered if your model gave any insight into the difference in mass between electrons and protons. I'd be fascinated to know what how you factored that into your model. The other thing is, I wondered, because you focused obviously on the nucleus, do you have any intention to move on to electrons and the shells?
Short answer, yes.
Good stuff. Care to elaborate while I'm here?
Yeah, we'll try. That's why we're here, right? I'm not sure, James, can we do that? Can you go back to carbon, please? 12, yeah. Oh, yeah, and the electrons, please, if you can. Anyhow, mass, you mentioned mass, and
Yeah.
so, right, thank you, James. So the electrons are there, which we see in yellow. I'm not saying this is an accurate depiction, if you will, because they're highly elusive, right? So we chose the best way we could. You can see that it makes deuterium pairs. You can see, so I'll point it out. This is one of the pairs, right? Now we have 6 pairs in carbon, and this is the internal structure. The outer electrons, which you alluded to, are determined by the internal structure, meaning there are certain places, if you will, where the outer electrons would take place, but at greater distance, in a simple way. So over here, if you project that outward in a larger orbital, if you will, about 10,000 times the diameter of the nucleus, that is where the outer electrons would be. So they take place, in my mind, in a static position, like a little hole in the ground, if you will, electrostatically. That's where the electron would land and want to sink down, if you will. So if I excite it, I excite an electron, and it wants to fall back to its ground state. And it will fall back into that dimple, if you will, of where it can be, where the charge is lacking, if you will. So we are definitely stepping up to that level. That's my answer first, but we cannot really do it yet, but it's definitely something we're aiming for. And the point I'm trying to make is that the outer electron structure, so meaning the orbital structure, if you will, is determined by the nucleus. So I hope to have answered your question that way.
Thank you. The distinction in mass, have you got any?
Mass. I was trying to avoid that. No, I know, it's very nice. Mass, well, Wallace Fornell has a lot to say about that, of course. First of all, mass is, of course, as Wallace pointed out, confused with matter. I've seen so many articles and papers and stuff, They go on about ESMC square, of course. I believe in ESMC square, mind you, but in a little different way. I believe the ESMC square is here. I believe, in a short way, matter cannot be created nor destroyed. Matter. Mass, yes, not matter. So I consider the proton and the electrons the matter, if you will. And the electrons are even debatable there. Mass, I believe, is a... well, let's go. I'm challenged, thank you. So, what we can see is this deuterium pair, right? Now, when the electron is there, and around this is a little toroidal structure, if you will, no matter what I do, another proton cannot, as you can see here, occupy that little bit of space, right? Now, that little bit of space belongs, if you will, now to the, this is hypothesizing, belongs to the deuterium. But there's a little bit of extra space, volume, if you will. That volume belongs to the deuterium. But the mass is reference to carbon-12. Again, carbon, most central. Carbon-12 means if I have 12 protons in the carbon-12, that's exactly an atomic mass of 12, meaning one proton is 1. Now, if I take into account that little bit of space, I get a distortion, because it's extra volume without the matter, without the proton. When we go to the hydrogen, for example, it has an atomic mass, it should be 1, right? If we have a straightforward correlation. But in reality it's 1.004 or something. I believe that the little bit of space which is blocked by the structure, which cannot be occupied by any other sphere, any other proton, that is averaging out the mass of one proton, if you will. That's where the mass defect comes from. Now, I cannot be sure. This is a challenge, and this is something that we're trying to do, what I alluded to at the presentation with the cold fusion community, for example. They are very, very much into mass defect, binding energy, etc., especially binding energy, they love it. So I believe mass is, or the mass defect, if you will, is a result of the structure, as I just tried to point out. So that little bit of space makes the average atomic weight number a little bit off. That's why we have this mass defect, or rather different numbers. To top it off, the binding energy is confused by that. Meaning a lot of this mass defect is turned around in quantum mechanics into binding energy, or the other way around. Meaning the two are mixed. It's not a pure number, if you will. We have two fundamental things going through one another. So I believe that we need to redo our homework collectively and figure out if something like this is actually true, and if we can explain correctly the mass defect for starters, and then do the binding energy correctly again. And then come up with accurate numbers, because the calculated numbers do not always, well, not entirely coincide with what we see and measure. So, hope to have answered your question.
I think this is one case where we may be able to return to Wilhelm Weber and his force law, because that force law becomes repulsive when the electron gets close to the proton, which means that the standard electrostatic law doesn't work. In that case, it may actually help explain this mass defect and so on as we get the numbers right. So I've given the book to, where is he? Peter Modell.
Yes,
He's
here.
I have managed to get a copy just before coming over here. I've only read part of it, but Peter was very interested. And I think you should have a look at it too before we go.
Definitely will.
Edwin, quick question.
Sure.
So you're saying the electron has a static position, more or less. So
Yes.
then my question then is, was the idea of rotating electrons, was that just an assumption somebody made because it's like the solar system, or was there any empirical evidence for it?
Very good question. Love to answer that one. To my knowledge, now I do not know all the intrinsic details like anybody else, but Mr. Bohr, I believe, that's the Bohr model, the planetary orbit, if you will, It works lovely when we look at just hydrogen, meaning one proton, one electron. Then there is no specific change. You can look at it in any way, it's always the same. So that's when the orbital model works. This is an old model. Now, what is very nice, what I learned throughout the past few years is that when I talk to electric engineers, they were all alluding to the fact, yeah, but electrons orbit the nucleus, right? They're convinced of this. And I come from a chemistry background, and I know that that was one of the atomic models, if you will, to look at it. But it comes from Bohr, and it's very old, and it's been done away with for a long time already. So I talked to Neil Thompson, and I said, well, Neil, why do you keep thinking this? I mean, this is not, this is not even being taught in physics and chemistry. And he says, well, yeah, it is. I said, no. I said, how did you get there? He said, well, at my education, electric engineering, they go into the atom for just a brief moment, and they say, well, this is the model, this is the nucleus, so we have some electrons, and they rotate around it, and that's about it. Let's continue to Maxwell's laws or whatever. That's it. So all these people are stuck with a wrong notion in their mind. Even in quantum mechanics, electrons do not orbit. They do not. They have orbitals, and the orbitals are like droplet shapes, and then they go into the chance and the statistics. Where is the electron? It should be there or there or there or there, and it's kind of like a droplet shape or whatever. But it's not rotating. Only in the hydrogen atom that would be the case, but rotating is just a different perspective from another side. So I hope to have answered your question there.
Yeah, you saying, look, this sort of orbital view of the electron going around the nucleus isn't correct, and you have to have these like static quantum mechanical shells. However, you see the model to make it work mathematically, you have to have an orbiting force, i.e. centrifugal force. So in a sense, the mathematics requires some sort of concept of motion.
Let me answer you by asking you a question. Why is that? Why do these equations need a rotating force?
Well, because you've got an attraction, and under Newton's second law of motion, we have F is, one over r squared is the attractive force, and you've got mv squared over r for to keep a thing in orbital motion, i.e. the acceleration towards the centre.
Could it be that this is where we go wrong, all of us? Could it be that
I'm asking you.
The disconnect is? This is something I asked myself, right?
Oh, okay. Well, that's what I'm asking you.
Well, I'm with you then.
You've answered nothing.
Well, no, I'm not trying to make...
Okay, no, I understand.
I think,
okay.
I truly believe whenever we look at what kind of evidence we have, right? Even if you were to do mainstream quantum mechanics, there are no orbiting things going on. And we may have models that kind of sort of work, but I was trying to point out that works for the electromagnetics in the EE engineering world. It doesn't mean it works for physical chemistry.
No. Well, I think that's important, you see, because we draw all these pictures of spheres, orbits and all that, but that's because we can understand that in terms of our real world, i.e. you, me and people running around each other in circles, right? But it doesn't actually mean that nature is that, whatever we mean by is.
Okay. I'll answer in a different way.
Okay.
When we all go to sleep here right now, we stop moving, breathing, etc. Everything is dead silence, including all the matter and materials. Not moving at all. There's no more energy, or rather the energy is slowly dissipating, falling to steady, nothing moving, right? Then we go into the atomic world, and suddenly they tell us we have a highly moving kind of solar system in the atomic world, with rapidly, light speed, rotating things, zipping in and out of existence things. My mind cannot follow that. And what I try to say is that in 2016, I believe it was, the European Physics Society something, are now acknowledging that that model, the orbiting or even the protons moving, cannot be true. Even mainstream quantum mechanics people, and I forgot the name, are now trying to depict the nucleus in a way that we can see and that it is structured. And they're not even acknowledging it yet, but they're trying to do it. So that's the fascinating part. So I would stick to the conviction from my part that I believe, but you can all please disagree, challenge me, keep challenging me, but I believe it's static in principle.
I've studied the history of physics, and the people like Niels Bohr, Einstein, and Heisenberg, and everybody else, when they were doing physics, they were working from Boskovich's theory, and they don't teach that at university to physics people anymore. What happened was they cut that out, so they had to make room for quantum mechanics and Einstein's relativity. So what they do is they cut out a vast chunk, about 100 years worth of physics, and they just teach a bit of Newton, jump to Maxwell and so forth, and then go on to the modern stuff. And they don't teach you how you get to how Niels Bohr and everybody else got onto the idea of what they were talking about. And if you go back to the history, what you've got from Newton, he was only considering particles acting under a attractive force. And the next step after that was to consider what would happen for particles acting under attractive and a repulsive force. And that was done by Boskovich. And this is just now totally missed out of what they teach people. And based on that, you've got a nucleus and you've got electrons going around it, you've got stable and unstable orbits. And that's where you get the quantum levels from. So they were working from that basic idea and building upon that. Because when they teach it, they don't teach that anymore. And so that causes a total disconnect of how did they get from, say, classical physics to what you got now. And so it's just amnesia of how they got to where they are, basically. And that what would have been my talk have been about.
Well, thank you for that contribution. Yeah, well,
This is one case where I think Wilhelm Weber has to be looked at because he produced a model of the atom which worked. It's based on an electric force theory which has an island of stability. In other words, you get beyond or below a certain radius and the electron then naturally goes into orbit and doesn't radiate. So that needs to be looked at. The other thing is that I'm a little skeptical of having static particles in any structure, because then one of the reasons the atomic model was successful was that it was spherically symmetric. And if we're going to have dipole forces from particles, they have to be spherically symmetric. They have to respond to the entire universe. So that means the nearest objects will form the strongest dipole, other objects will form multiple electrostatic forces between them. Having a static object can't do that.
well, interesting. Okay, I have a few opportunities to go into stuff. James, can you put up radon and make a sideways view? Uranium is speculation right now. It's getting there. Turn a little. Yeah, thank you. That's perfect. A little bit back. Thank you. Up. So what we can see is not entirely spherical. That's one. The structure causes it to be a little bit elongated, disc shape, if you will. It's a bit flattened. That's one. Another one is iron, 26.
I should point out, by the way, I'm talking about the individual particles, the protons and electrons, not the entire
Right.
structure.
Right. I'm with you there. But I'm going to take it to the atomic level, if you will. It gives me an opportunity to talk about that. Thank you. So, first we see here this little bit of flattened shape. Now iron, if we look at it from above, James, you already know, iron is normally, well, let's start. We have groundwater everywhere. There's a lot of iron in it. And when it's dissolved, it's in the 2+ state. When water comes up, like in a well, it reaches the oxygen of the air, meaning an oxygenized environment. aerobic instead of anaerobic. Now iron is, has a nice little speciality to it. When it's dissolved in the groundwater, it's in the 2+ state. Nothing else, not like I have a valence of 2 or 3 or 4 and it can be several, as often is the case. No, iron is specific. I'm 2+, it says. When it reaches an oxygenized environment, it becomes 3+. Meaning a chemical environment changes the physical properties of that specific element. So there's a lot of dynamics still going on, right? It's static in principle, but there is a lot of dynamics. What can happen, I believe, is that when the iron connects in a chemical way to the oxygen, the chemists amongst us have learned that the oxygen is much more electronegative. It wants to pull in that electron from the other one, in this case iron. So we have oxygen is a -2 and the iron is a +2. It's a nice connection there. So it connects on this side, in comes with 2 connections, comes in the oxygen. This is a lithium, and a lithium is a +1+. I have 2 of them. And it is a 1+ because there's 1 too much electron there, or rather it could use another proton to balance out very evenly. Meaning it's a little bit too negative, this one. Therefore, it becomes a plus because it releases 1 electron, valence electron, and then the nucleus becomes plus. That's why we say iron is a 2+ ion, because it released an ion, an electron. So oxygen comes in, makes a connection to the iron. The electron is pulled from this lithium towards the oxygen, and similar here. Now I do get a dipole, because this side of the iron, the negative goes away, so it's a little bit too positive now on this side. It needs to rebalance. Static in principle, but there's a lot going on. We have on the other side, to make it complex, we have 2 neutral connections, and this light green depicts an extra neutron, and they are there for reasons of construction and stability and balance, right? It needs to be balanced. If I take those 2 away, it's too lopsided. It starts to decay into a shape that is balanced again. Now, in the connection with the oxygen, as I pointed out, that the polarity starts to exist. And it pulls, I believe, and again, this is hypothesizing, if you will. I believe that one of those neutrons over here ends up over here. It's being pulled in a little bit towards the right due to the chemistry. When that one reaches over there, you get another red one like this, another lithium. Now I have 3 times 1+, 3+.
I just want to make a comment. He has said that there are no neutrons, and when Edwin talks about a neutron, he really means a proton and an electron pair. So some protons, in order for them to stick to the atom, they need to bring an electron with them because there's no negative charge for them to stick. So when he says a neutron, he's saying a proton that has to have an additional electron in order for there to be the charge for it to stick. It really isn't the conventional neutron.
So, yeah, spot on. Thank you, James. So when the nucleus has enough negative charge, you could add another proton, right? Like James pointed out. If the nucleus is in a state meaning a specific number of protons, electrons, there's many times it cannot do that, so it needs that extra electron becoming the extra neutron, right? So I hope that. Questions? Say again. It's the outer electron, if you will, from the iron. Yeah.
Can we go back to the iron model? And if we look at the periodic tables, all elements have certain crystal structures. Now, iron is I just looked it up on the periodic table, is central cubic. How would you take this iron model and make a central cubic crystal out of it? If we look at an iron crystal, you know, not as just the atom, but the complete crystal structure of...
Right, the crystalline structure, if you will.
Yes.
Right. Well, I cannot specifically answer. I can see the relationships, if you will. What we do need, and I'm not trying to make it easy here, but we do need to advance this model further to that level, if you will. Right? So what we have right now is the nucleus. Next step will be the position of the outer electrons, if you will. And from that point on, we need to exactly figure, there's always a lot to discover. Let me point that out first. This is a structure, this model, I'm studying it myself, right? I'm trying to find stuff, not because I want to find stuff, but because there is so much to find. These structures are like little telltale things with full of hints and clues of what is actually going on, constantly related to the properties of the elements. So exactly how that happens, I'm not sure. But if I can look just a little bit further, if we have a carbonate, for example, a CO3, right, in sandstone. The C is in the center and the free oxygens are like a tetrahedral shape almost on the 1, 2, 3 sides. And it kind of makes a sphere on its own, again, a spherical thing. And everything tries to be spherical, which I call the densest packing principle. So the nucleus itself wants to be a sphere, right, a densest packed sphere, and this is where most people go like, okay, we have a big sphere with many of these protons, and it's one chaotic blob. Well, that's where we divert. It's not a chaotic blob, and it's still a spherical thing, close to it, but with a specific structure.
Yeah.
And the forces keep balancing out. Now, the outer structure will determine the crystalline structure.
That's exactly the point that I was trying to make. You know, if you have a structure, you know, it would be nice if the sort of structure would immediately give rise to the crystalline structure.
Can I just say, I mean, from the picture I see, you have 4 corners.
Basically, yeah, four points that stick out furthest from the center of the sphere, if you will. Yeah. Right. Only several points, the red ones in this case, is where the proton electrons are still not balanced out as in the noble gaseous state, right? Meaning, nice point to make. Chemistry, valence electrons has to do with this. The red is red, it's active because there's still a positive charge here. A positive point, if you will. The polarity, that's what's going on. It's not noble, it's not complete. So those icosahedron, dodecahedron shape is not complete yet. Because we have a carbon here, carbon in the center, and a carbon there. And these shapes will become a carbon on their own, on the next level, if you will, the bigger atom again.
Now, as you know, I'm quite interested in alchemy. I mean, wouldn't we all be? You know, turn it into gold, eh? But what's always struck me as being very peculiar about nuclear physics is you can have decay, for example, uranium-238 to 235, and that gives out energy, which we can use to make electricity. Or you could have fusion, as in a hydrogen bomb, and that gives out energy. Now, as I understand it, and correct me if I'm wrong, didn't Newton have a law that said there's always conservation of energy, which then becomes conservation of energy and mass really equals mc squared? I would have thought that if you're building matter, building up larger and larger atomic nuclei, you'd be putting energy in. It'd be endothermic. And if you're splitting them, you'd be releasing energy, which is exothermic. But it seems whatever you do, you get more energy. Have you got any comments on that?
Yes, I can allude to that. The tipping point is at iron. Iron and nickel, that's where the tipping point is. So elements below iron, smaller than iron, when I put them together, I get an excess heat. So the fusion yields heat. Above iron, fusion does not yield heat anymore. It becomes an endothermic reaction, uses heat to make it happen. And this exactly has to do with transmutations. So when we have a lot of energy, like in a magma environment, that energy can be used to create heavier elements than iron. Right now, that is only possible by an exploding neutron star, something like that. That extra energy then creates the heavier elements. That's the mainstream story. Now, the energy that's released has to do also with the mass defect and the binding energy we were alluding to earlier on. So there's a confusion there. But what I'm saying is the tipping point is at iron. So when these branches get bigger and bigger and bigger, James, can you put up a really large one again? Radon, whatever. We can see that the branches start to divert more and more and more. So if we take the whole nucleus as one sphere, it becomes more and more porous, if you will, right? Less protons per volume. And at a certain point, a tipping point, just about at iron, is where it's no longer pays off to add something to that structure. So the red one becomes also one, and you get this here. So there's more space there. It becomes more unstable. There's too little electron protons per volume, if you will,
Yeah,
to keep
but-
your structure intact. And the tipping point is at iron.
Right. Okay. Well, let's go back before iron. Yesterday we were talking about if you added, I think it was carbon with oxygen, was it, to make silicon?
Yes.
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 So if I took my silicon atom and I wanted to split it to make carbon and oxygen, I would need to put energy in.
Most likely, yes. Exactly. That's the reverse. Below iron, that's the reverse. You need energy to destroy it.
Right. Okay.
Questions?
How does your model cope with different isotopes of the same element?
Isotopes. Well, let's stick with carbon. There's carbon 13, and if we now make one more step, we get carbon 14. Thank you, James. Can you turn it a little bit to the, so that's on both sides, the neutron, if you will. Right. This would be carbon 14. Carbon 14 is the radioactive thing that we use for dating, right? Now, it's okay as long as one neutron is on that side and one neutron is on that side. And we get the carbon 14 pre-decay. The next one, James. Yeah. This is what would happen. So we get a carbon still with two neutrons, but something like a neutrino or whatever, gamma ray, maybe even heat, I don't know, electric polarity, there are many things we could point to that makes this happen. So I don't believe radioactive decay is chance-based at all. Chance-based in the sense of which one do I hit? Yeah, sure, but not in the total. There's an external component that pushes that little thing across a threshold, a little bump, if you will. Then the reaction takes place and totally depends on whether it's exothermic or endothermic, right? Now, these two here are going to come together, and then we reach nitrogen, because a carbon 14 decays into a nitrogen. Now we can see the two made a pair. To make a pair with two neutrons, remember a neutron is a proton plus an electron, I have two of those, so I have two protons, two electrons. That's too much for a deuterium pair. So this green is now another deuterium pair with one electron in between. The outer electron is simply booted out into the orbital structure. This principle follows exactly mainstream nuclear decay steps everywhere. Every isotope you look at, this stays true in this model. Now, there's a change there, and exactly how that works we need to find out, right? But this is an important change. This is how the isotopes work, and isotopes can only be in a specific number per element, totally depending on the structure of the nucleus. Is there room for an extra neutron? And an extra neutron is halfway of the next step to the next element. So it's in between, if you will, right? And if I put in two, self-organizing system, it will decay to nitrogen. Self-organizing. Exactly how that works, I'd love to find out.
Yeah, I think this idea that the environment affects essentially the rate of decay of the carbon-14 is really an amazing idea. So this must be testable, because you could cut carbon-14 in one situation and carbon-14 in another box with a different environment. And it's possible now to measure the rate at which they are decaying. So there's another experiment for Sapphire Project here.
I thank you so much for pointing that out, because that is, of course, a state where I want to go, that there is experimental evidence to prove all of this, right? That's why I call myself a studier of this model as well. So, yeah, thank you very much for that. Yeah, totally.
Any more questions?
I don't know, but I thank you so much for your attention and for challenging me, and keep doing it. And please keep in mind, I am a study of this model myself. I may have made errors, right? Many errors. I don't think fundamentally that much. I think the principle sticks, if you will. We created a lot of elements. The more complex they become, the more difficult it is to verify, if you will, from certain angles, okay, this is really it. One of the verifications is the valence factor. Another is, of course, the number of protons, neutrons, etc. So the heavier the elements become, the more difficult it is for me to discern if it's really that the correct shape.
This is a work in progress and you are studying it yourself. It seems reasonably accessible to the childlike mind which is age 7. So how can you make it, and you've got the app, which is awesome, how can children who want to study it with you feed back?
Magnets, give me 1 sec, please.
And be guided for the things that they're having, because they will have to learn it alongside the standard model, so they will always slightly get confused when the two clang together, and will need help to keep them both separated and keep asking their questions to both models, okay, without being upset about
I thank you so much for this, I almost forgot. I believe, because this is first of all visual, right? One picture is worth 1,000,000 words. That's one. Second of all, it's very simple in principle. Right? It's not difficult to understand. But if you go into all the properties and the calculations and the numbers, we get quite a complex thing again. So it's all there. The numbers are there too, right? And we're working on it, work in progress. But to come back to your point of children, you can mimic these nuclei with magnets. Everybody loves magnets. They're awesome to play with. You can mimic them, so you can feel in your hands, especially for children. You can feel in your hand what it is. You can let them make them.
I needed to buy another packet. I needed to buy extra packets of, whatever it was, red ones and white ones. I think white was oxygen or something. And it was appalling. We could ever only make like 2 atoms, and then we were, So these nucleates, they're all the same size, and they will stay in the shape that you've said that they will stay in. I won't suddenly find that the kid's crying because it went into a ball. Okay.
Well, the fun thing is when you create a carbon, the blue, with the magnets, and you have it in your hand, the center is hollow. It's icosahedron, right? And the center is hollow. There's almost room for another one, almost, but it's not there. Now, when you have that shape in your hands, you suddenly feel the strength of that shape, suddenly. Totally balanced out, platonic solid, right? And you can feel it's strong. So, it's not just seeing it, but it's also feeling it. And especially with children, I believe this is so important, to give them some understanding and give them some enthusiasm back for science. James, may I ask you to give a very, very short thing? You were so keenly interested in science when you were young, I believe, and then something happened.
I was a child, I was very interested in science. I have a trash can of the solar system from when I was 8 years old, and it's one of my most valuable possessions. But when I got to be high school age, I was reading about quarks and charms and ups and downs, and I lost it. I wasn't smart enough, I couldn't figure it out, and it didn't make sense. And so I went into computers. I wrote this program here. But when I started number 1, the electric universe was the first step to saying that maybe science is actually fun again. But now I can visualize these atoms in my head. I can see how they fit together, and it really has brought the fun back to chemistry for me. But I'd like to make a comment. When we were at the Leonard conference a couple weeks ago, there were 30 models about the nucleus of the atom. And they all come from the particle physics, quarks and charms and ups and downs, and they're trying to figure out how an element works based on these teeny tiny particles. This was the only theory that came from the other side, came from chemistry, and tried to figure out the nucleus of the atom based on chemistry.
When you make a mistake with building with magnets, the magnets are, they have no mercy. In the beginning I had that a lot before I even met James, so I was playing with these magnets and doing all this stuff and research and whatnot, and I found the correlation, and I found that, damn, these magnets actually, they kind of sort of follow the same building principle, and you can feel it. Now if you make a mistake, that's your nuclear reaction. It's self-organizing, so I make a mistake, I put one extra magnet there, the shape starts to distort and it's impossible to correct it again. You get a nuclear decay reaction. If you do it on the right spot and you follow the logic, you don't need force, I don't have to force anything. It's very delicate, very delicate. It just falls on itself, no problem. That's how we build them with the magnets. If you made a mistake, especially in the beginning, they're utterly no mercy. It will destroy it and you have to start again. Now if you want to make a bigger element, iron or whatever, or a little bit bigger, it becomes tedious to rebuild that thing and try to avoid that same mistake again. So it's very educational and punishing, meaning you do the right thing next time.
I remember my point. Edwin worked on this for 10 years before I met him. I met him 2 years ago, and we've been working on this program. And what we really found is that the model is teaching us. There were those 30 models I mentioned that were at these other models. They're running supercomputer simulations to try to find something that gets close to the numbers we want. And this thing just grows in the shape. We don't make up, we don't fudge things, we don't try to put, well, what if we try it here? We follow a very simple set of rules. And the atoms pretty much build themselves. And we'd really like to build a program, we call it the auto builder, where we give it some parameters and say, okay, show us all possible arrangements that meet these requirements. And we really think we can do it, where we won't build these things. It's self-organizing. It should build itself. So that's one of our goals.
Thank you very much.